All right, welcome. Today, we are jumping headfirst into what's basically a high-tech detective story. You know our planet's massive frozen regions, right? The glaciers, the ice sheets? Well, they're changing. But how do we actually know that? I mean, how on earth do you track something so gigantic, so far away and so incredibly important to, well, everything? The answer, you'll see, is way up there, hundreds of kilometers above us, with satellites that are literally taking the planet's pulse.
And yeah, that's the big question for today, isn't it? It sounds like something straight out of science fiction, but it's one of the most vital fields in Earth science right now. We're talking about measuring the movement of ice, sometimes down to the millimeter, from a satellite that's just screaming past at thousands of kilometers an hour. So how in the world is that even possible?
Okay, before we get into the how, let's talk about the why. Why does this even matter? Look at this number, 2,720 gigatons. That's the estimated ice mass that the Antarctic ice sheet has lost in just a few decades. And just so you get the scale here, 1 gigaton is a billion metric tons. It's a staggering amount. And get this, about 80% of that loss, it came from just one area, West Antarctica. So yeah, these aren't just numbers on a slide. They are telling us about huge changes to our planet. And that's why taking its pulse from space is so important.
To really get why the technology is so cool, you first have to appreciate the problem. Glaciers are like the planet's frozen pulse. They're slow, they're powerful, and they are incredibly sensitive to what's happening with our climate. But trying to keep tabs on them from the ground, that's a monumental task. You're dealing with some of the most remote and hostile places on Earth.
I mean, just think about it. You've got this steep, treacherous terrain, bone-chilling temperatures, and for half the year, the poles are plunged into complete darkness. And on top of all that, your typical satellite camera is totally useless if it's cloudy. So what we really needed was a tool that could just slice through all of those problems, the clouds, the dark, the distance, and give us a really clear, consistent picture of what's going on.
And that brings us to our detective's secret weapon, synthetic aperture radar, or SAR for short. This is the technology that gives us that planetary scale vision. And believe me, it completely changed the game for studying ice.
You know, the easiest way to think about SAR is to imagine a bat's echolocation, but strapped to a satellite. See, it doesn't need sunlight. Instead, it fires out its own little pulse of microwave energy. That pulse travels down to the surface, bounces off whatever's there, and then travels back up to the satellite. By recording what that reflected signal looks like, SAR can paint this incredibly detailed picture of the ground. Whether it's day or night, clear or cloudy, it's amazing.
And these features, well, they're basically SAR's superpowers. It sees right through clouds and darkness, which is a must-have for the polar regions. Scientists can even tune it to different wavelengths, L, C, and X band, to either see deeper or get a sharper look at different kinds of surfaces. But the most critical part is that it gives us two key pieces of information. Intensity, that's how strong the signal is when it comes back, and phase. And phase is the really mind-bending part. It's the exact point in the wave cycle that returns to the satellite. And that little piece of information, it's the key to everything.
So, having a tool like SAR is one thing, but the real detective work, the real magic, is in how you use the data. Scientists are basically playing a giant cosmic game of spot the difference, looking at how the ice has changed between two pictures taken by the satellite.
And they have two main tricks up their sleeve. The first is called INSAR, or interferometry. This is the super precise tool in the toolkit. Remember the phase of the radar wave? Well, INSAR compares the phase from two images taken at different times, and from that, it can measure movement down to the millimeter. It's wild. The second method is offset tracking. This is the tool you pull out for the big, fast stuff. It doesn't use phase, it uses the intensity of the image, tracking features like big cracks in the ice or even just random speckle patterns as they move from one picture to the next. So yeah, INSAR is for dusting for fingerprints, and offset tracking is for chasing the getaway car.
The precision of INSAR is it's staggering. And it's not just for ice. This technique is so sensitive that people use it to see the ground in cities sinking because of groundwater pumping, or to watch a volcano's sides bulge by just a few millimeters as magma moves around underneath. We're talking about measuring changes that are completely invisible to the human eye.
But there are places where INSAR just can't keep up. On the fastest moving glaciers, the surface changes so much that the delicate phase signal just turns into noise. That's where offset tracking shines. It basically plays a feature matching game. It'll grab a small patch of the first image and then hunt for that exact same patch in the second image to see how far it's moved. This is how we can track ice that's moving several meters in a single day.
Of course, it's never quite that easy, is it?
In our detective story, the evidence from space can get a little smudged, a little blurry, making it tough to read. And scientists have had to figure out how to deal with some pretty big challenges to get a clear picture. Okay, so the #1 enemy for INSAR is something called decorrelation. Basically, if the ground changes too much between satellite visits, maybe some snow melted or there was a fresh snowfall or the ice just moved too fast, that precious phase signal turns into random static. Poof, measurement gone. Then you've got the atmosphere itself. Pockets of water vapor can actually slow down the radar signal, which can trick you into thinking the ground is moving when it isn't. And last but not least, the sheer amount of data. Modern satellites are like a fire hose of information, and just wrangling all of it is a huge challenge.
This quote here from a really important paper kind of sums it all up. It all comes down to something called coherence, how stable that radar signal is over time. The moment you lose coherence, you lose the measurement. And on a living, breathing glacier, coherence can be a really, really fragile thing.
But, when faced with these big problems, scientists did what they do best. They got clever. They came up with smarter ways to solve the mystery, combining different techniques and using new technology to get a clearer picture than they ever had before.
And this is the brilliant solution. Take a super important, fast-moving glacier like Pine Island in West Antarctica. The main trunk of the glacier is moving way too fast for INSAR. It just decorrelates instantly. But the rock around it and the slower ice on the edges, they're perfect for it. So what scientists do is use INSAR for the slow parts, and then use offset tracking for the speedy central core. Then they just stitch those two maps together, creating one complete, seamless, and super accurate map of how the entire glacier is flowing. It's truly the best of both worlds.
And at the same time, the tools we have in space have gotten so much better. Back in the 90s, satellites might fly over the same spot every 3 to 35 days. Now, the Sentinel-1 satellites revisit most places on Earth every 6 to 12 days. And here's the best part. The data is totally free and open for anyone to use. There are even commercial satellites that can get images in less than 12 hours. Getting pictures that frequently is a total game changer because it gives the ground less time to change and decorrelate.
And the breakthroughs aren't just happening up in space. To handle that absolute flood of data coming down, scientists have basically moved their entire workflow onto powerful cloud computing platforms. And now they're even bringing in AI and deep learning to help automate the analysis, letting them spot important changes almost as soon as they happen.
So, okay, we've got these amazing tools, these brilliant techniques. But this isn't just about cool tech. Let's wrap this story up and talk about why this all matters so much in the real world. Why do we care about watching ice move from space?
Well, for one thing, it's about water. In places like high mountain Asia, you've got hundreds of millions of people who rely on rivers that are fed by glaciers. As you can see here, the water in those rivers comes from rain, from snowmelt, and critically, from glacier melt. So knowing exactly how fast that glacier component is changing is absolutely essential for managing water for all those people.
It's also about a hidden process going on inside the ice sheets. You see, the top layer isn't solid ice. It's a thick layer of old, compacted snow called firn, and the best way to think about firn is like a giant, icy sponge. When the surface melts in the summer, this porous firn layer can actually soak up and refreeze enormous amounts of that water.
How much are we talking about? Well, right now, about half, 50%, of all the meltwater on the surface of Greenland, it's caught by this firn layer. It doesn't even make it to the ocean. So it's this incredibly important buffer that's protecting us from faster sea level rise. The problem is, as it gets warmer, that sponge is starting to get waterlogged. Since 1980, the firn has lost about 5% of its ability to store water. As it gets more and more saturated, more of that meltwater is going to run straight into the sea. And that really brings us to the final, most important point. All of this detective work, measuring speed, tracking elevation, understanding how meltwater moves, it all provides the ground truth. These are the real-world facts that we plug into our climate models. This data has shown us that ice sheets can change way faster than we ever thought possible, and it is absolutely crucial for making good, reliable predictions about one of the biggest consequences of a warming planet, future sea level rise.
You know, for the very first time in human history, we have the power to monitor the pulse of our entire planet. We can watch its most remote, most vital systems change, almost in real time. This technology has given us a perspective that was just unimaginable a generation ago. And so that leaves us with a pretty profound question. Now that we can see it all so clearly, what are we going to do with what we see?